Let's go over all of the problem-solving techniques in A-level physics. In this video, I'm going to be covering everything I know about the real specifics of problem-solving. Firstly, we must make note of the command word in the question. We're going to start off with the command word state. These problems can typically be subdivided into a couple of categories, either a definition or a numerical value. If it's a definition, make sure to recall it correctly and make note in your preparation of any words that are underlined for your exam board in the mark scheme. For instance, in the definition of the superposition of waves, we must state that superposition occurs when two or more waves interact and the resultant displacement is the sum of the individual displacements. If it's a numerical question for 1 mark as part of a longer question, there typically is not going to be a lot of working out. So consider some values such as 0. In this particular case, we have two forces which are equal, therefore the resultant force on Y during this collision event will be 0. Or in this question, if we have an oil drop which has been suspended between two plates of an electric field, the magnitude of the electric force can be stated directly to be equal to the weight. On to the next example, which is show questions. These can typically be divided into two categories. Some of them are on derivations that you know and they're part of the specification. On the other hand, you may be given an unfamiliar expression and you can use your knowledge of physics to arrive at it. When the command word is show, we must, well, show as much of the working as possible. For instance, if we had to show that the value of the escape velocity of an object from a planet is given by this expression, we can start off by saying that the kinetic energy of an object, a half mv squared, plus its potential energy, which is given by minus gmm over r, where r is the distance, they all have to add up to 0. Then I'm going to say that a half mv squared is equal to gmm over r. I'm going to cancel out the m's, and I'm going to rearrange for v squared, which is going to be given by 2gm over r, meaning that v will be given by the square root of 2gm over r as required. Let's do a slightly longer one, and that is Kepler's third law, showing that t squared is proportional to r cubed. So for escape velocity, we looked at energies, and for the orbital time period, the square of it, we need to look at forces. So to show that the square of the orbital time period is proportional to r cubed, we must look at the gravitational force, which is then going to be equal to the net centripetal force, which is m omega squared multiplied by r. The gravitational force, this here is just a subscript by the way, is just going to be given by its magnitude, which is gmm over r squared is equal to m omega squared multiplied by r. We can cancel out the m's, and then we can bring the r over here, and then we're going to get that gm is equal to omega squared r cubed. Given that omega is 2 pi over t, we can say that gm is brackets 2 pi over t squared, multiply this by r cubed. And then we can do one final rearrangement. We can go that t squared will be given by 4 pi squared, divide that by gm r cubed, and we have shown this in clear steps, starting from one end and then going all the way to the answer. What we should really avoid is writing out bits of the answer sort of here, here, or here. We want our answers to flow really nicely from one end to the final answer. The other type of show question that is likely to appear on the exam are on novel and unfamiliar physics. For instance, you may be given an equation that you've never seen before, and you may be asked to manipulate it or use your knowledge of physics to show that this is true. Let's have a look at an example just like this. We have this circuit with EMF E, internal resistance little r, and then some resistance capital R, and we need to show that this expression is actually true. Now, you've probably never come across this expression in that exact form, but we can use the laws of physics to arrive at it fairly easily. I'm going to start off just by saying that the EMF is equal to I multiplied by R plus R, the external plus the internal resistance. In almost all exam boards, this formula is given. Let me know if you'd like me to derive this in the comments. Okay, so let's just rearrange for I, which is just going to be given by I, divide that by R plus R. Now let's flip both sides, and then what we're going to get is that 1 over I will be equal to R plus R divided by E, and then we can just follow through and say that 1 over I will be equal to R over E plus the internal resistance divided by the EMF, and this is what this expression here looks like. Let's do a harder example. So we have this typical circuit with internal resistance, and we have a wire with resistivity given by rho, internal resistance little r. The cell has an EMF given by epsilon. So we need to show that this expression is true. Notice that it immediately seems really similar to the one we've just done, which is from a completely different paper, from a completely different year, which goes to show you that practice works because you tend to spot patterns between questions. Anyway, so how are we going to tackle this? I'm going to start off by saying that the EMF will be equal to the current multiplied by the external resistance plus the internal resistance. Then I'm going to rearrange for the current, which is just going to be equal to the EMF divided by R plus R. Then 1 over I will be equal to R plus R divided by the EMF. Notice how I am showing each step really carefully and methodically. Okay, now we can use the algebra trick that this here will be equal to R divided by the EMF plus the internal resistance divided by the EMF. But we also know that R is equal to the resistivity multiplied by the length divided by the surface area, which is given by pi d over 2 squared. Okay, well, this here will be equal to rho L, and then over pi d squared. Now the factor of a half here will end up in the numerator, so we're going to get a factor of 2 squared, which is 4. Okay, then I'm going to draw a little arrow to show that I've substituted back into the previous equation, and what we are going to get, I'm just going to carry on this side, is that 1 over I will be equal to R, which is just 4 rho L divided by pi d squared, and then we also have a factor of divided by epsilon, so this goes in here, plus R over epsilon. Well, look at this is exactly what we needed to show here. Please note that this is not an equation that I've come across before, even in my teaching, but it's relatively easy to get to it by being really methodical. Also include all the equal signs as you're going through the derivation. We can also get show questions which involve a final value. It is really important to show our calculations. So in this case, we need to show that the magnitude of the deceleration is given by this value. Well, we need to carefully write down our equations because this is a question about an electron that is moving between two plates within a magnetic field. So what I'm going to do is write down that F is equal to the electric field multiplied by the charge, but the net force is equal to mass times acceleration, which is equal to the electric field, which is given by V over D multiplied by the charge. So the acceleration will just be given by VQ over dm. We're ready to plug in some values. So the voltage in this question was 0.3 volts. The charge of an electron is 1.6 times by 10 to the power of minus 19 divided by the distance, which is given by 6 millimeters. So be careful with the units. 6 times 10 to the power of minus 3 multiplied by the mass, 9.11 times 10 to the power of minus 31. Plugging this into a calculator, we are going to get around 8.78 8 times by 10 to the power of 12 meters per second squared, which is about sort of 8.8 times by 10 to the power of 12, and we've successfully shown this. Occasionally, we need to show proportionality from a graph. The technique is always the same, and it involves picking some points from the graph. In this case, we have a graph of charge against distance, and we need to use the figure to propose and carry out a test to show that Q is inversely proportional to D. Well, if Q is indeed inversely proportional to D, then there's some constant of proportionality right over here. So this means that Q times D will be a constant. Now we can verify this by picking two values of Q and D and multiply to see if they're constant. The values need to be corresponding. So for instance, I can pick Q to be, let's say, 10 nanocoulombs. So we're going to have this one over here, and that's going to correspond to a value somewhere over here like this. And then I can pick, let's say, 20, which is going to be this one over here, which is going to correspond to a value somewhere over here. Let's call this one 1.3 centimeters, and shall we just call this one 2.6? So if Q times D is equal to a constant, then 20 nanocoulombs times 10 to the power of minus 9, multiply this by 1.3 times by 10 to the power of minus 2. This here will just give me 2.6, multiply this by 10 to the power of minus 10. For our second test, all we need to do is multiply this value by this value. So let's see what would that give me. That's be 10 times 10 to the power of minus 9. Multiply this by 2.6 times 10 to the power of minus 2. We can already see that this is going to give us exactly the same result up to two significant figures, which is 2.6 times 10 to the power of minus 10 coulomb meters. An important final step, just in case, because this can often be the mark, would be actually to write down that conclusion. So in this case, the values are the same, meaning that Q is inversely proportional to D. Please note that if this was a table of results, or if this was a 3 or a 4 marker, I might have picked some extra points to ensure that this is actually correct. Very often the number of marks do correspond to the number of calculations needed, but not always. Moving on to the next command word, which is describe. Describe means essentially tell me what you see. If we have a graph of velocity against time, we are asked to describe this relationship, we can say that the velocity of the object is directly proportional to time. An even better way of saying this is that the velocity increases linearly with time. This means that the acceleration is actually constant. What we should definitely stay away from, though, are vague expressions such as when time increases, the velocity increases. We need to be as specific as possible. Now, if we are asked to explain this, which is another command word, we have to tell the reason why that is happening. For instance, this graph here is telling us that the acceleration is constant. Well, a reason why, let's say, a car might be moving at a constant acceleration is that a constant net force is being applied, which leads to a constant acceleration because the net force is equal to the mass times acceleration. Well, here's that exact example from a past paper on the difference between describe and explain. So we need to do two things: describe and explain the motion of an object falling at terminal velocity, and this will be for 3 marks. So at terminal velocity, the object is traveling at constant velocity. And now we're going to explain why that is the case. Well, there is 0 resultant force. And just to be absolutely sure to get all the marks, I'm also going to write an equation for it. Notice that we could also have included things like upthrust, but their effect might be negligible. Occasionally we get completely table questions. Sometimes we have to calculate a value and put that value in the appropriate column. The thing to watch out for is that we need to be consistent with the amount of decimal places that is already given in the table. Very often we also have to criticize the recording of some results. The most obvious error, which is almost always present, is inconsistency in the amount of decimal places. For instance, we can see how all of these are given up to 3 decimal places, and over here this reading only up to 1. Another tricky one is writing down directly quantities which have actually been calculated. So there is no easy way to measure directly the extension. In this case, because this is the classic Hooke's law experiment, to measure extension, we needed to have recorded really 2 values. So something like x2 measured in meters and then x1 measured in meters, because the extension, let's call it E, is just actually equal to x2 take away x1. So that's a definite problem with this data. Suggest questions can be tricky. They can have some freedom in the answers. It's really important to stick to the fundamentals and write or suggest facts about physics which are going to have the consequence that is asked in the question. Let's have a look at an example. Back to this question, we can see that we've got a lovely suggest question. So the terminal velocity of a small sphere of density rho s and radius r falling through a fluid of density rho f is given by this new formula, where this is a constant, g is the acceleration. So water droplets of rainfall fall to the ground, whereas water droplets in mist appear to float. Use the formula to suggest why. So floating in this case would actually mean that their speed is equal to 0. Now, the only way this can be 0 is if the density of the sphere is approximately equal to the density of the fluid. And this makes physical sense because the density of the drop, if it's surrounded by mist, which is also water, the 2 densities should be similar. In air, though, the density of the sphere, i.e. the drop, will be a lot bigger than the density of the fluid, giving us some terminal speed. In suggest questions, I always try to over-explain a little bit and showcase knowledge of physics and mathematics that directly relates to this question. Sometimes in exams, though, the word suggest is used almost interchangeably with explain. So for instance, here we need to suggest why the powder piles up and the nodes within the tube. Well, the nodes have 0 amplitude, so the powder is not displaced. Occasionally we also get single-step calculations. Those typically require a single line of working out. However, some of them may have a trick. Watch out for unit conversions, for instance from kilometers or miles per hour to meters per second. Or potentially a unit error which might cost you a nice and easy mark otherwise. This might seem really basic, but I see quite a lot of people doing this in inefficient ways. Say that we wanted to convert 5 centimeters squared to meters squared. One trick that I know is to place some brackets over here. This then turns into 5, and then centi is just a mathematical power, 10 to the power of minus 2 meters squared. So this here will just then be equal to 5 multiplied by 10 to the power of minus 4 meters squared. And look how quick unit conversions suddenly become. So let's say we had 7.0, I don't know, let's say micrometers cubed. Well, this here will be equal to 7.0 times by 10 to the power of minus 6 meters cubed, which is 7.0 times by 10 to the power of minus 6 times 3 is 18 meters cubed. Talking about units, a really important technique is working with base units. As an example, we're going to find the SI base units of Planck's constant. We're always going to follow exactly the same steps. The first step would be to simply write an equation for the quantity. Here's one. We can say that E is equal to HF. The next step would be to rearrange for the quantity. Okay, this means that H will be equal to E over F. Then we're going to express each term in base units. For instance, in this case, the base unit of energy is kilograms meters squared s to the power of -2. Side note, but how do I know that? I always pick an equation for energy, I don't know, a half mv squared, for instance. So the half has no units. This is kilogram. Speed is in meters per second squared, giving me kilograms meter squared s to a power of -2. The units of frequency we're going to need to divide by that is 1 over seconds. So this thing here will be equal to kilograms meter squared s to a power of -2, multiply this by s, giving me a final answer for the base units of h, which is kilograms meter squared s to a power of -1. The next one is crucial, and I see this in every single A-star student that I've taught over the years. To avoid errors in calculations, write down the formula first, then plug in all the values from the actual question. Finally, write down exactly what you're going to input into the calculator, leading us to the final answer. This can feel counterintuitive compared to what you've been used to GCSE, but it will make a massive difference because it's going to leave a trail of your working out. Should you get an answer that you know it's wrong, you'll be able to go back and see exactly what you've put into the calculator. Additionally, just simply writing out the formula that involves a square makes it harder to potentially miss that step. Whenever I do a silly error, typically it's because I've tried to rush and do multiple steps in my head rather than write things out clearly. On to the harder questions, which are probably most important for A-level physics. Yes, multi-step calculations that can be anywhere from a single multiple choice that requires a lot of work for 1 mark all the way to some 5-mark monster of a question. Here are lots of techniques to help us with them. A technique which is often overlooked is actually working backwards in a question. Let's say that you need to calculate a specific quantity, write down an equation for that very quantity, and then work backwards to see if you can spot what you're given in the question that could eventually lead you to that. If the question gives you a hint of energy, for instance, kinetic energy, then typically using energy conservation tends to help. Sometimes in energy conservations, we're not actually given the mass, but typically, for instance, if potential energy near the Earth was converted to kinetic energy, the mass tends to cancel. A super important energy conservation equation is actually for the acceleration of electrons, and if you're ever given the speed of an electron that's been accelerated by, let's say, 5,000 volts, you can use this equation that EV is equal to a half mv squared. This here is the electrical energy that was transferred directly to kinetic energy, where V is the supply voltage, lowercase v is the speed, this is the mass of an electron, this here is the charge. If it's a different particle, we can adjust either the mass or the charge accordingly. With multiple choice questions, it's really important to realize that there is no single magical trick that can help you be really good at them. The only way to get really good at multiple choice questions is to understand the physics really well and be able to apply it quickly. The good news though is that they can be trained really effectively. Number one, practice working out problems in symbols, as this is a really common mistake in multiple choice questions physics. Here's an example of a problem that we have to work symbolically. So we have two wires, Y and Z, that are joined together. One has a cross-sectional area 2A and then twice the length as well. Wire Z is fixed, and then we apply a force to both of the wires. Which of the following is the extension of wire Z? First of all, massive clue, they're made out of the same material. This here simply means that they have the same Young's modulus. If something is the same for both wires, so elements, then what I like to do is set them equal to one another. So I'm going to write this in quite a lot of detail. I'm going to say that the Young's modulus, I've just called it E, of Y has to be equal to the Young's modulus of wire Z. Okay, well, Young's modulus is force over cross-sectional area divided by the extension, which is X, divided by the original length L. And this is equal to the same force, which is applied to the cross-sectional area of Z, which is just 2A. Now we're going to divide this by the extension of wire Z. I'm just going to call this X Z, and this is another technique which is really useful. Just call something a letter in your equation, even if it's not there, if you think that you need it, and then divide it by 2L. Well, hang on a minute, we can actually see that the factors of 2 are just going to end up cancelling. So X, we could even rearrange that if we wanted to, but the two extensions will have to be identical. Mathematically, if we're really interested, that's going to cancel, that's going to cancel, that's going to cancel, that's going to cancel, that's going to cancel. Then if we were to flip the fraction, we're going to get that xz has to be equal to x. Well, this here corresponds to the correct answer, being C. One incredibly useful technique for multiple choice questions and in general about forces is the drawing of a free body diagram. So for instance, here we've got a raindrop that is falling through the air with an increasing velocity, and we have some forces which act on it. So I'm going to immediately draw my raindrop, and then we have W, which is acting downwards. We also know that there will be some upthrust like so, and some viscous drag, which they've just called F. Because the drop is falling down with increasing velocity, we know that the resultant force has to be in the downward direction, meaning that W has to be greater than F plus U. So this here corresponds to the correct answer, being D. Now, the technique that I'm about to show you is a massive last resort. So first I'm going to do this problem in the way that it's not supposed to be done. But have you ever guessed a question in multiple choice and have you just guessed at random? So don't do this. What you should do instead is get rid of at least one, ideally two options, and that will massively increase your chances. For instance, in this case, they're asking us for the expression for the upthrust on the sphere. Now, upthrust is a type of force. So if it's a force, it must have some sort of units of force. The units of force being F is equal to ma. This is kilograms meters per second squared. So this over here, 4 pi, no units, meters, and then density is just mass over volume, so there's no seconds. So if I was in a rush, I had no idea, I had not revised upthrust, I know that the answer is not going to be A. And now I have improved my odds massively if I was to guess. We could even increase our odds to 50-50 just by doing a little bit of thinking. Now imagine that I have a sphere and it's surrounded by some sort of a medium. Let's say it's in water. Now, how much upthrust it will experience will definitely going to depend on the density of that material, which in this case is given by the letter rho and then a subscript L, rho L. So it's most likely not going to be equal to this one because this does not have the density of the liquid in there. Okay, so it's either C or D. Now we could even just use units. Once again, I'm pretending that I know nothing about upthrust, just what I would do in this case. Well, the units that I need to get are kilograms, meters, s to the power of -2. So if I have meters cubed multiplied by the units of density, which are kilograms, per meter cubed, multiplied by ms to the power of -2. Well, look at this, they cancel, and those units here give me the units of force, so the correct answer has to be C, even just by units. Of course, by the way, the proper way to do this question is just to remember Archimedes' principle that says that the upthrust is equal to the weight of the fluid that's been displaced, which is equal to the mass of the fluid multiplied by g, which is equal to the density of the fluid multiplied by the volume of the fluid multiplied by g, which is going to be equal to volume is 4/3 pi r cubed, assuming spherical symmetry, rho f multiplied by g. A really vital technique for A-level problem solving is also the use of ratios. Remember, whenever we have a ratio, this is just a division sign and things will tend to cancel. In this case, we've got a couple of wires, we're given the Young's modulus, and then we need to find a ratio of the two extensions. My first job would be just to see if I can provide an expression for the extension in terms of Young's modulus. Okay, so over here on the side, I'm just going to call the Young's modulus E. So in general, E was force over area. This is stress divided by the strain, which is equal to the extension divided by the length. We're ready to complete our ratio. So the extension of x, well, I'm just going to write this as a fraction as f over a, the cross-sectional area of x, divided by Young's modulus of x. Do they both have the same Young's modulus? No, they don't. So Ex divided by the length. Now, this here is just the extension of x. Then I'm going to divide by the extension of y, which is the same as multiplying by the inverse. So multiply this by EY divided by L. They do have the same length, same original length, and then the inverse will have a denominator, which is going to be given by F divided by the cross-sectional area of Y. In a way, this here that I'm going to put into some red brackets just to differentiate it for you guys is the inverse, or 1 over the extension of y. Okay, now we're ready to cancel lots of things out. So F is going to go, L is going to go. And we can also see that the ratio of the cross-sectional areas is just 1 to 2. So this here will actually equal to 1 over EX, which is 120. It's gigapascals, but all the units will end up cancelling out because it's a ratio. And this here will then be multiplied by EY, which is just 200 divided by. Now we have to be quite careful with the ratio because this is 1 over AY, so this is 1 over 2. So this factor here will end up going in the numerator, so this here will actually be equal to 400 divided by 120, i.e. the correct answer must be D. This here is a technique in questions for potential dividers. Typically it's used in multiple choice, but it can appear lots in written questions as well. So whenever we have a potential divider like so, and they're asking us to talk about resistance and potential difference, my advice is to always consider the RIFC. In other words, resistance in the circuit, current, the fixed resistor, and then potentially what happens over the component, for instance, the thermistor or the LDR or whatever is connected. Let me show you what I mean. So the intensity of the light intensity increases. So the resistance of the LDR is going to do the opposite. In general, the thermistor also does the opposite to the temperature. In both cases, the graph of resistance against, let's say, light intensity looks something like this. So as light intensity increases, resistance decreases. Anyways, we can put a little arrow down here. Now, in general, the resistance in this series circuit will decrease. That will mean by default that the current will increase. Okay, well, across the fixed resistor, V is equal to IR. So if the resistance R is fixed, i.e. it's a constant, If the current has increased, then the voltage across the fixed resistor should increase as well. We can clearly see that the answer to this question is B. Now, if we were to take the question even further and say, what happens to the voltage across the LDR? Well, if the voltage across the resistor increases by Kirchhoff's second law, they have to add up to the EMF in the circuit, so that here must decrease. We need to acknowledge that occasionally in multiple choice questions, we get some which take a considerable amount of work for a single mark. This is typically balanced because in the same paper you will also have questions that are simple recall questions that might only take you a few seconds to do. If you're ever wondering if you should attempt these harder questions, my answer is always yes. In fact, before we actually start the question, we never know if it will turn out to be really tricky or not so tricky. We might even spot a nice easy method of eliminating most of the answers and then choosing between one of them. On the topic of time though, it is absolutely crucial to do the past papers under time conditions, and this will really help you, especially with the tactics in multiple choice questions. After each past paper, remember to analyze your performance so that you can improve to the next one. And now let's move on to experimental questions. These can also be split into two categories. Some of those you would have done in the lab and you'll be very familiar with, or you would have done a really simple experiment adjusted for the equipment in your school. The other one are completely novel experiments. Do not worry, these seem intimidating at first because you've not seen an equation or a situation, but you can always use your knowledge of physics to explain exactly what's happening. If it's a 6-marker question, it's really important to note down all of the command words. Then you can start structuring your paragraph with those command words in place. This will make it easy for the examiner to mark. It will make it easy for you not to actually miss any important details. Bullet pointing is absolutely fine. In fact, I encourage it because it's a really organized way of listing what needs to be written. Let's do this 6-marker. So we have this experiment with a microwave transmitter that's being reflected at a metal sheet. And then we're given some values. The distance between adjacent regions of maximum and minimum is 72 millimeters. What we need to do is two things. So explain the presence of the regions of the maxima and the minima. So this is our first command word, which is simply to explain. Our second part is to determine the frequency. In other words, to see if we can calculate the frequency. My first paragraph is going to contain the word explain or explanation. So why are there regions of maxima and minima? Regardless of this situation, regardless of what integral details and diagram they might have given us, the only way that maxima and minima are actually formed is via superposition. Now I'm going to make a comment on the maxima and the minima. So maxima are always caused by constructive interference, whereas minima are caused by destructive interference. This is actually really the formation of a stationary wave with nodes and antinodes, and the maximas are also caused by waves that are in phase, and the minima, the nodes, are caused by regions in which the waves are in antiphase. I want to get all the available marks, so I'm going to make sure to write this. This is plenty of detail, and I'm going to leave potentially a little bit of space in the real exam just to add things if I think of them. But for the calculation, I am also going to set this up in a different paragraph. This will also help the person marking the paper because it will be very clear and easy to award the marks for the explanation and for the calculation. Okay, so we're given the distance between adjacent regions of maximum and minimum intensities. I always tend to just draw a little graph. So let's say this one here is a max, like that. This here is a minimum. Well, they differ by a quarter of the wavelength. So this means that 72 millimeters is equal to lambda over 4. Now, to calculate the frequency, we can just use the fact that speed is equal to f lambda, meaning that the frequency is just going to be c over lambda, which is going to be 3.0 times by 10 to the power of 8, divided by lambda, which is just going to be equal to 72 multiplied by 10 to the power of minus 3, multiply this by 4. This here is just going to give me 1.04 multiplied by 10 to the power of 9 hertz. Now, my final tactic for a 6 marker is just to have a look through the question, see if I have missed something or if there's anything else that I can add. So we just needed to explain, check, the maximum and the minimum, check. One thing I'm going to add is that a stationary wave is formed. So I don't think I've actually written this. So I can just write this over here that a stationary wave is formed. One more really important clue is that whenever an A-level physics question asks you to describe how you would carry out an experiment to verify the relationship between r and theta, well, this here is a clue that we should plot a graph of r against theta. We could then use y equals mx plus c analysis to determine k. In this particular example, there was a different equation that was given. But in all cases, if the question asks analyze the relationship between r and theta, we should always plot an appropriate graph. Please note that the sentence that if the graph is a straight line through the origin, the relationship is correct often appears in math schemes. There are certain statements in A-level physics, part of the content, which are virtually guaranteed to give you marks. And this is precisely why you should watch this video in which I go over statements from the entire specification that are almost guaranteed to give you marks. Click over here.